Lesson 7, Geometric Probability. One of the more straightforward lessons here. You've already learned some basic probability stuff. Favorable outcomes divided by possible outcomes. I'm just going to throw a little bit of geometry in with it. So we're going to throw a dart at the board. Now we're going to assume that the dart definitely hits somewhere on the square board. Okay, but it's totally at random. Right? Now in real life, sometimes you throw a dart and you completely miss the board. Or if you're a good dart player, it's more likely you'll be closer to the center. But we're just assuming that any dart automatically will hit the board, but we have no clue where it's going to hit. It's equally likely to hit anywhere. So are we more likely to get 10 points or 0 points? Well, what's the probability of getting 10 points? You know, remember our notation. If I could put that P, we know it means probability. And then if I had an event called event A, I could have put P of A, but I didn't label this event as being event A or anything, so I just put, 10 points. Well, I need to know the area of that circle that's noted as being worth 10 points. So that's a small circle on there. But then I also need to know the area of the entire target, which is a square. Now, the smallest circle looks like it has a radius of 3, so that's kind of easy to figure out. But the square might be a little bit trickier to see at first. It looks like from the center of the board to the edge is going to be 3 plus 3 plus 3, which is 9 inches. Which means each side of that square is actually 18 inches. Right, so pi r squared for that small circle, radius is 3. For the square board, length times width basically becomes side times side, or side squared, so 18 squared. 3 times 3 is 9. I can do that in my head. 18 times 18, I'm going to grab a calculator. All right. I'm not doing 18 times 18 in my head. And I'm thinking, you know what? Since I'm going to try to compare two different answers, I'm kind of paranoid about trying to find a common denominator, or even if I already have a common denominator, when I get some weird numbers like pi in the numerator, I'm like, I don't know about this. This is one of the few times I'd recommend converting to a decimal, because we just want to know which one's larger. So maybe you recognize that 9 over 324 reduces to 1 over 36. If not, just do 9 times pi divided by 324. It'll be the same as pi divided by 36. It comes out to be approximately 0.08. All right, because if I'm trying to figure out which of these is going to be larger, I don't want to have to try fight to get a common denominator. Or even if I'm so lucky to get a common denominator, I don't want to try to figure out which numerator is larger. So, convert to decimals. Probability of getting 0. Well, it looks like I have to be outside that largest circle. So, probability of 0 points to be the area outside the largest circle divided by the area of the entire board. So I'm lucky with the denominator, right? We would have had a common denominator, so I would say, hey, cool, we'd have a common denominator, but look at the crazy numerator here. What's the area outside of that largest circle? Well, I guess it's the area of the square minus the area of that largest circle. So, again, I'm looking at this really bizarre 324 minus 81 pi. I don't know, is that more than 9 pi? Is that less than 9 pi? I don't know. So, hey, yeah, let's convert this to a decimal. Okay, I think I got Tinkerbell quiet down and stopped barking. So 324 divided by 324, I could reduce that to 4 over 4. If you're wondering why it didn't get reduced to 1 over 1, well, I want a common denominator, and 81 over 324 is 1/4. If all that just seems like gibberish to you, you probably would have grabbed a calculator and done 324. Subtract 81 times pi, gotten an answer, and divided by 324. It'd be identical to 4 minus pi, get an answer, divide by 4. Comes out to be about 0.2. Alright, so since I'm trying to compare these, I'm like, well, which one's larger? Well, 0.2 is much larger. So I'd be more likely, because 0.2 is a lot larger than 0.08, I'd be more likely to come up with 10 points. I'm sorry, I'd be more likely to come up with 0 points instead of 10 points. And if you kind of look at the picture, you kind of say, well, gee, it's kind of like I got the 4 different corners up there that count as 0. And yeah, they look like they're bigger than that bullseye if you put them all together. Alright, so geometric probability, often you're finding the area in a picture or various areas in a picture to compare them. Or you might even just have like a number line. Or, in this case, a segment of a number line. Problem with a number line is that it goes on forever, which would be an infinite length, and infinite is not going to work with probability. Now, a trap here is that students might say, hey, you know what? If I count from 40 to 60, I'm counting 21 different numbers there. And if I look at 42, 43, 44, that's 3 different numbers. So 3 divided by 21 reduces to 1/7. Problem with that is you got to remember on a number line, there's actually an infinite number of different points I could use. Right, so if I'm talking about between 42 and 44, I could do 42.3. I could do 43.06597. Right, I mean, there's a whole bunch of numbers. So that's why instead I got to say, hey, no, I'm not going to just count the 21 numbers I see, or count the 3 integers that are 42, 43, 44. I have to actually look at the actual distance of those segments. If you're wondering about the word inclusive, it means we include the endpoints. So you see 40 to 60 inclusive, that means 40 can be chosen, 60 can be chosen. If instead it said exclusive, then we would not be able to pick 40 or 60. Same thing with the 42 and 44. Inclusive means you can actually pick 42, you can actually pick 44. If it said exclusive, you would not be able to pick 42. Now you can pick 42.000001, because that's larger than 42, but you wouldn't be able to actually pick 42. So for the probability of 42 to 44, I actually need the length of the segment from 42 to 44 over the length of the segment from 40 to 60. So even though there are 3 different numbers, so if I'm thinking about 42, 43, 44, the length of that segment is just 2. And although there are 21 numbers, if I start at 40 and count to 60, right, there are 10 numbers from 40 to 49. There are 10 numbers from 50 to 59. That's 20 numbers. Ooh, and then there's that number 60. That's 21. Right? So if I try to count the individual numbers, I would have 3 over 21. But that's not what is happening here, right? I need the length of those segments. From 40 to 42, that has a length of 2. 40 to 60, that has a length of 20. That reduces to 1/10. All right, so if you're working with a segment of a number line, make sure you're actually finding the distances and not just counting individual numbers. And since this is the final PowerPoint of the year, I thought we might want to stroll down memory lane and say goodbye to some of our characters we came across. The vast majority of the images that I use on PowerPoints, I shamelessly steal off of the internet. And while I stole that spider cat from the internet, I spent way too much time doing this spider cat on my own. Way too much time. And of course, in the great debate of what is the more awesome animal, the cat or the cow, we got to include spider cow, which of course I just stole off the internet. And so IXL X7 geometric probability, and that is the last PowerPoint of the school year. That doesn't mean we're done with math, but this is the last PowerPoint.